Differential equations look mysterious, and there's a reason for that, which is they are mysterious. So we want to take some of the mystery away. You need to keep in mind that differential equations started as models. So you've seen about Newton's law of cooling, and so that's a model of what happens when you put a sweet potato into the oven or something like that. Now, the abstract people started off with models, and then they went kind of nuts saying, oh, let me put anything over here. And so then we get these kind of abstract differential equations, and they may or may not be models of something. Sometimes it's kind of fun to try to think of a model that a certain differential equation might model. Think of a situation that it might model. But sometimes you can't, and sometimes people just do them, you're not going to believe me on this, for the sheer joy of doing it. But mostly it's because it's useful. So what I'm going to do is I'm going to write down a differential equation, and I'm going to pull the solution from behind my ear. The exact solution to this uses techniques that we don't get to study in a one-semester course. But what we will do is demonstrate that what I write down is in fact a solution. And then what we're going to do is graph these functions. There's more than one solution to any differential equation. We're going to graph a few of them, and so that'll be a good review of some of the graphing techniques using the mean value theorem. And then we're going to look at the graph and find some features that will help us work with differential equations in a way that we can do when we can't do the exact solution. Most differential equations that are solved in the universe are done approximately, so that's the way to think about it. What you really want to be thinking about is models, but I've been racking my brain all day. I haven't figured out a model that this equation model, or a situation. So the equation I want to write down is, it's pretty simple. It's this. So we're going to take some unknown function y, and the derivative of y is x minus y. It's the difference of the two coordinates, and you'd think you'd come up with something with that, but that's not the case. And so as a differential equation, this doesn't make any sense. So let me pull out from behind my ear the solutions. And then we'll see that they're the solutions. And I hope that seeing some solutions will help convince you that this isn't such a bizarre thing. Most of the computer time in the world, the part that isn't used on kittens and naked people, is used on solving differential equations. And so this is how we come to understand the universe. So the solutions that I came up with are this. It's a function. I'm just going to call it y. I'm not going to give it a separate name. And the equation is x minus 1. Now that's not so bad. Now comes the bad part. Plus c, and it's traditionally use a capital C here. And in a couple of weeks when we do integration, you'll see y. E to the minus x. So this is a function. It's the kind of function that people study in calculus, and it's got a linear part and an exponential part, and we can actually do some stuff just by saying that right there. So now the thing is, we're claiming that this is a solution for every value of the constant or parameter c. So let's look at that. So the equation says that the derivative of y should be x minus y. So what I'm going to do is I'm going to take the derivative of y and then do a little algebra, not very much, and we'll see that the derivative is in fact x minus y. So these are solutions. So let's see, y prime is 1 minus 0, I'm not going to write that down, minus c e to the minus x. So that's just the derivative of x is 1, the derivative of 1 is 0, the derivative of c e to the minus x is minus c e to the minus x because of the chain rule. And so there's y prime. And then I'm going to compare that with x minus y. So that's x minus, do the parentheses first, and I'm going to fill in the parentheses with y, x minus 1 plus ce to the minus x. And I skipped something very important here. I'm going to go back. I don't know that these are equal yet, so I'm going to put a question mark over the equal sign to indicate to everybody, including myself, that this is a question. I'm trying to see if this is equal. Okay, so back to what I wrote down, and it's a very small amount of algebra, and y prime is, well, let's see, x minus y is, I'm just doing the algebra here, is 1, that it's x minus x, that cancels, minus 1 is 1, minus c e to the minus x. And so what I've got an equation, and I calculated both sides, and I got the same thing on both sides. So this equation is true. So that's what it means to have a solution or solutions to a differential equation, and so we have some solutions to this. So before we get too carried away with abstract stuff, which we don't do too much abstract stuff in a one semester course, let's look at these functions. Y is equal to x minus 1 plus ce to the minus x. And I want to point out two things about this kind of a basic shape thing, a qualitative thing, without doing a lot of calculations. And so one is, well, they both involve what happened to this exponential term. So we get two things that happen here. If x is really big, that means that e to the minus x is about 0, so that doesn't count. It doesn't count very much, or it may not count within our ability, the number of significant figures that we have. So that means that c e to the minus x is approximately 0, and so y is approximately x minus 1. So in fact, what that's saying there is that we've got an asymptote off on the right saying that as x gets really big, this graph gets closer and closer to the graph of y equals x minus 1. So that's a graph that we understand, so we'll do that. In fact, I think what I'll do is I'll straight away do some graphing kind of stuff, and I might as well throw in the graph of that line. And I'm going to do it in green because I grabbed a green pen first. The green has nothing to do with asymptotes, but it's dotted, and there's the asymptote, y equals 1 minus x. I'm sorry, I wrote the wrong thing. It's x minus 1. I was saying, wait a second, that would have a negative slope, but in fact that has a positive slope. That's good. Okay. And we know when x is big that y, this function that we've kind of come up with, is very, very close to being x minus 1. The other part of the qualitative analysis is that if x is really negative, that means that c times e to the minus x is huge. You've got e to now a positive power. X is negative, minus x is positive, and it's huge. And so basically the x minus 1 part doesn't count. So x minus 1 is irrelevant. So that tells us a lot of stuff that I can just kind of pencil in. I won't pencil it in, but out here, the curves are getting closer and closer to the asymptote. And out here, they're coming down real fast, or coming up real fast, depending on the sign of C. And so that's something that we can already say about these functions without ever having actually done anything at all. Okay. But now we do have the derivative, and we do have the mean value theorem, which we use in the form that says that if y prime is positive, then y is increasing. So let's see what the derivative tells us about this. Well, we already did the derivative. We know that y prime is 1 minus c times e to the minus x. And while we're there, let's take y double prime and that is c times e to the minus x. And that has the same sign as c. So the thing is, c is this unknown parameter. So if you pick a positive one, then y double prime is positive, so y is concave up. If you picked a negative value of c, then y double prime is negative, and so the graph is concave down. So let's just make a note here, same sign as c. And for the first derivative, we've got 1 minus c times e to the minus x. And so there are a couple of different ways to look at that. If x is really big, then e to the minus x is 0, so y prime is 1. That's also kind of saying that we've got this asymptote here. So y prime isn't 1, it's approximately 1. So there's the situation. And to be a little bit more specific, when things are in the small range, the thing with exponential functions is that if you're far from the origin, you know what's going on. On one side it's infinite, and on the other side it's 0. But you need to deal with the part that's close to the origin, and so let's do that. So anyway, so I've got y prime is 1 minus c e to the minus x. And one thing that happens I've written this down backwards in my notes, so I'm wondering if I'm going to get in trouble. Well, let's see what happens. If c is less than 0, then minus c e to the minus x is positive, and so that means that y prime is positive. I wrote the wrong thing again. I guess I'm just attracted to negative things today. So if c is less than 0, then y prime is positive. So I've got c here, and if c is less than 0, then I've got 1 plus something, so we're positive. And if c is bigger than 0, then what you find is, remember, c is something that you're going to pick. You get to pick that. And so if you pick a positive one, you're going to get one kind of behavior. And if you pick a negative one, you get slightly different behavior. Okay. So if c is bigger than 0, then what's going to happen here is that this is going to change sign, because what you're going to get is when x is really negative, then you're subtracting off, so y prime would be negative. And if x is really positive, then this is about 0, so y prime is positive. So y prime switches from negative to positive. And we knew that because we know that y double prime has the same sign as c, and so that's the concavity. And if c is positive, then y double prime is positive, and the graph is concave up, which means that it switches from being decreasing to increasing, or that the derivative is increasing. So that's quite consistent. Okay, so now comes the moment of truth, and this is something that people find kind of mysterious, but we'll see what goes on, and practice a little bit. So if c is positive, maybe we should step back and say how we find out what c is. Well, we get c is by looking at y of 0. So when x is 0, y is 0 minus 1 plus c, so it's c minus 1. So I probably should have said that earlier. So all I've done there is plug x equals 0 into this expression, and I get minus 1 plus c, because e to the 0 is 1. And so c is, you pick a starting point, and c is 1 more than that. So if I pick a starting point here, I just pick something kind of arbitrary. C is 1 more than that, and so that c is positive, and so we're going to get this behavior change. We're going to have a concave up thing that is asymptotic to y equals x minus 1. And if we pick a slightly different c, as long as we're still in the positive realm. We have concave up, and again, an asymptote. And just once you get into this, you can really get into it. So here are a bunch of solutions. These are depending on different values of C. So I can't, the paper isn't big enough to draw the asymptote all the way out. On the other hand, when C is negative, the graph is concave down and increasing, but still asymptotic. And so these are, let me label these, color code them. C is greater than 0. If C is less than 0, so that means we're starting down here, so one more doesn't get us up into the positive, then what we're seeing is a graph like this. I'm doing these in green. So that's what happens if C is less than 0. And that all depends on that initial solution, what happened when X was 0. So this is what the graph looks like. Kind of, I like it. It's kind of pretty. And so there are two different flavors to it. And the peppermint is the concave up, and the wintergreen is the concave down. It's getting close to dinner time. I'm getting hungry. Okay. So this is what we have done. We've used some calculus. We've used some qualitative reasoning. We've used what we know about exponential functions, and we're able to graph all of these solutions, and we've got some pretty good graphs. So let me draw one or two more solutions a lot bigger. One of the things that is one of my big desires in life is to have big graphs. So I'm gonna draw a couple of solutions. I've just picked a couple out arbitrarily. And so this is the value when X is 0. That would make C positive. This is the value when X is 0. For the green one, that would make C negative. And what I'm going to do is go back to the differential equation. So remember, I pulled this solution out of my head. No, I actually had to do some work, but I'm not showing you the work because it involves techniques we haven't studied yet. So I have the solution. We verified that it is the solution. We graphed the solutions, and we've seemed to have lost track of the differential equation. So let's go back and see what that is supposed to be telling us and how we can see the reflection of that on these graphs. And so there's the situation. So here's the differential equation here. This dy dx is equal to x minus y. And so that tells us if we have a specific point on the graph, then that tells us what the slope of the tangent is. Now, we don't need that because we have the solutions, but let's see what that would tell us. So let's see what's going on here and why this graph reflects it. So what I'm doing is kind of drawing in the tangent line approximation here. The next thing we're going to do is reverse this. We're going to start with the tangent line approximations and try to reconstruct the whole curve. So it's not as tangent as it could be, but that's okay. So what we have here is that y is it's kind of hard to tell. Anyway, we're saying here that x minus y is positive. And as we move out and we go a little bit further in the x direction, we're seeing that x minus y is more positive. And if we come back over here where x is negative and y is positive, then x minus y is negative. And so we're seeing little tangent lines with negative slopes. So the x minus y corresponds to what we're seeing on these graphs. To turn this around, what we're going to do is draw all the x minus y's, draw little segments with slope x minus y, and then kind of fit the curve through it. And let me do one more here. In the green case, everything appears to be positive. So where I'm at with this one, I've got a fairly big x and a smaller y, so x minus y is positive. There's no scale on this. This isn't a real graph. Every real graph has to have a scale. This is qualitative. But if you look at what we're seeing here and play around with it some, you'll see that, here we have a situation where x is small and y is big, and the slope is really negative. X minus y is negative. Here we have a situation where x is big and y is smaller, and the slope is positive, and yet that's reflected in these graphs. So the aim really is to turn this around, not to pull out a solution, because most differential equations can't be solved exactly anyway. So we're not just going to pull out a solution. What we're going to do is say, hey, you know what? I know the tangent line here. I know the tangent line here. I know the tangent line here. And kind of fair those together, F-A-I-R, and we'll be able to get an idea of what the solutions look like. So that's a whole nother situation. But for the moment, let's just see what's happened here. We started with a differential equation that's kind of abstract. Most of the ones that we see are models, like Newton's law of cooling. And I told you what the solutions are. We verified the solutions. That's an important step, that you know that any of these functions really solves this equation. And then we took the derivatives. Now I took the derivatives from the solutions. Let's just take a second and back up and take the solutions. Just a reminder, we've got y prime is x minus y. And so without even knowing the solutions, I can take y double prime, and that'll be kind of interesting. Y double prime is 1 minus y prime, which is 1 minus the quantity x minus y. And so if we have any particular xy coordinates in mind, we can tell what the concavity is. Anyway, so we did the graphing thing. We took the derivative, we took the second derivative, we looked at increasing, we looked at decreasing regions where the function was increasing or decreasing. We looked at the concavity of the graph. But then the twist here now is that we've gone back and looked at these little tangent lines and verified that they were the tangent lines that the differential equation specifies. The differential equation says the tangent at the point xy has slope x minus y, and that's a very, very powerful piece of information about the function, and so we would like to take advantage of that.